Okay, so welcome to the Mrs. Baker's walkthrough of the guided notes for Lesson 5, simple calculations involving the mole. And for this, we are going to just be using the mass mole MR triangle. We're just going to be hanging out in this red triangle up here. What mass of calcium oxide would be obtained by heating 25 grams of limestone? So we plug into the table method what the question tells us already. We know we have 25 grams of limestone. We can work out the relative molecular mass because calcium is 40, carbon is 12, and oxygen is 3. So we have 16 times 3. If we plug that into our calculator, 40 plus 12 plus 16 times 3 gives us 100. To work out our number of moles, we must do the mass divided by the MR. That will give us our number of moles. So 25 over 100 gives us 0.25. Now we look at our molar ratio. It's a 1-to-1 ratio. So if I've got 0.25 moles of that, I've got 0.25 moles of that. I can work out my molecular mass in this column. I can say 40 plus 16 gives me 56. So to work out my final mass, I just need to do the MR times by the mole. So 56 times by 0.25. I've already got 0.25 on my calculator, so I just do times by 56, and that gives me 14. So the answer, what mass of calcium oxide would be obtained by heating 25 grams of limestone? Simple, 14 grams. Let's look at the next one. Titanium is manufactured by heating titanium 6 chloride with sodium. What mass of sodium is required to produce 1 ton of titanium? So again, we don't worry about the fact it's in tons. It just means that our answer is in tons. Let's plug in what the question tells us. It says we have 1 ton of titanium. Well, our periodic table tells us that titanium has a relative molecular mass of 48, and there's just one of them. So 1 divided by 48 gives us 0.02 moles. 0.02 moles. Now I have a 4-to-1 ratio. So I have 4 times as much sodium as I do titanium. So I must take my 0.02 and I must times it by 4. That gives me 0.08. So I'll say 0.02 times by 4 gives me 0.08. The relative molecular mass of sodium is 23. Now remember, it's not 4 times sodium because in the moles row, we use the big numbers as the molar ratio, and in the MR row, we're talking just about the mass of this one. So we're talking about just one sodium, no subscript numbers. Here we use small numbers. There's no subscript numbers in this case. It's just 4 lots of one sodium. So one sodium is 23, or 0.08 times by 23 gives us 1.91. So we have 1.91 tons of sodium if we need 1.191 tons of sodium if we would like to make 1 ton of titanium. Okay, this question is telling us that 2.67 grams of aluminium chloride was dissolved in water and an excess of silver nitrate solution was added to give a precipitate of silver chloride. That's all very interesting information, but the fact that it tells us that we have an excess of silver nitrate means that we can't use the moles of silver nitrate because we have more than we can possibly use. So we just ignore it. What mass of silver chloride precipitate would be formed? So we are looking to find the mass of the silver chloride. So we need to balance the equation first. I've got one aluminium over here. I've got one aluminium over here. I've got one silver over here, one silver over here. I've got 3 chlorides over here. So I need to balance my chlorides here by putting 3 there. Remember, I can't add small numbers because that's a chemical formula, and I'm not God. I can't mess with the chemical formula. So I've now got 3 silvers, so I need to put 3 silvers over here. That also goes to balancing my nitrates because I've got 3 nitrates over there. So that looks perfectly balanced to me. So here I need to make sure that I put a big 3 here as well because that is my molar ratio. My molar ratio is 1 to 3. I've got, for every 1 mole of aluminium chloride I've got 3 moles of silver chloride. Now let's plug in what the question tells us. The question tells us I've got 2.67 grams of aluminium chloride. I can work out the relative molecular mass with aluminium being 27 and chlorine being 35.5, and I have 3 of them. So let's plug that into my calculator. I've got 3 times 35.5, and then I'm going to add the 27 for the aluminium. That gives me 133.5. Therefore, 2.67 divided by 133.5, we know that because it's the mass divided by the MR gives us the moles. So 2.67 grams divided by 133.5 gives us 0.02 moles. Now, because of my 1 to 3 ratio, I must times this number of moles by 3. So I'll just times by 3, given my molar ratio, to make 0.06. I can already work out my relative molecular mass of silver chloride because silver is 108 and chloride is 35.5. I've got 1 of each. So 108 added to 35.5 gives me 113.5. Now I just need to times those two together because I need MR times the moles to give the mass. So I times by 0.06, and that gives me 6.81. Therefore, what mass of silver chloride would be formed? 6.81 grams. Well, that's as hard as it's ever going to get in the exam. But if you were hungry for a bit more of a challenge, we can do a stretch and challenge activity by looking at what mass of hydrogen is produced when 192 grams of magnesium is reacted with hydrochloric acid. First, again, the equation has been balanced for you, so that's quite nice. So let's have a look. I've got 192 grams of magnesium. The relative molecular mass of magnesium is 24, and I can also work out the I don't need to have, silly me, I don't need to have the hydrogen chloride in here. I need to have the hydrogen because it's saying what mass of hydrogen. So I can work out the relative molecular mass of hydrogen. Hydrogen is 2 because it's 1 times 2. So 192 divided by 24 gives me 8 moles. I've got a 1-to-1 ratio because I've got 1 mole of that for every 1 mole of that. So I must have 8 moles of that. I times that by 2 to give me 16 grams of hydrogen. What mass of oxygen is needed to react with 8.5 grams of hydrogen sulfide? So again, the equation is already balanced. I just plug in what the question wants. It's looking for what mass of oxygen, and it's told me that I've got 8.5 grams of hydrogen sulfide. So I've got 8.5 grams. The relative molecular mass is 2 times 1 plus whatever sulfur is. Sulfur is 32 plus 32. That gives me 34. So 8.5 divided by 34 gives me 0.25. I've got a 2 to 3 ratio. So I can't do a straightforward swap between my ratios. So what I need to do is find out what 1 mole is worth over here. So I'm going to do, to find out my moles over here, I'm going to do 0.25 divide by 2. That gives me 0.125 if my ratio was 1. But my ratio isn't 1, it's 3, so I'm then just going to times that by 3 to get it back into the other ratio. Times that by 3, and that gives me 0.375. Now I can work out my relative molecular mass of oxygen. So oxygen is 16 times 2 because there's 2 of them, which gives me 32. So I'm going to keep my moles on my calculator. I'm just going to times it by 32, and that gives me 12. So what mass of oxygen is needed? 12 grams. What mass of potassium oxide is formed when 7.8 grams of potassium is burned in oxygen? So we've got 7.8. Let's highlight what we've got. What mass of potassium oxide is formed when 7.8 grams of potassium is burned in oxygen? So we've got 7.8 grams of potassium. The MR of potassium is 39. So 7.8 divided by 39 gives 0.2. I've got a 4 to 2 ratio. Well, 4 to 2 simplified is 2 to 1. That's the simplest version. So if I've got 0.2 moles of potassium, I need 0.2 divided by 2. That gives me 0.1. The MR of potassium oxide is 2 times 39 plus 16. Well, 2 times 39 gives me 78. Added to the 16 gives me 94. 94 times by 0.1 gives me 9.4. So what mass of potassium oxide is formed? 9.4 grams. Railway lines are welded together by a thermite reaction, which produces molten iron. What mass of iron is formed from 1 kilogram of iron oxide? So we've got 1 kilogram of iron oxide. The relative molecular mass of iron oxide is 56 times 2 plus 16 times 3. Let's do that on our calculator. 56 times 2 plus 16 times 3 gives 160. Well, 1 divided by 160 will give us our moles, 0.00625. 0.00625. My molar ratio is 1 to 2, so I've got double the amount of iron, so I just times that by 2 to get my moles of iron. So 0.00625 times by 2 gives me 0.0125. My relative molecular mass of iron is just 56 because there's no small numbers. So I times this by 56. That gives me 0.7. So what mass of iron is formed? 0.7 tons. What mass of oxygen is required to oxidize 10 grams of ammonia? So what mass of oxygen is required to oxidize 10 grams of ammonia? So I've got 10 grams of ammonia. Ammonia is 1 nitrogen, which is 14, plus 3 hydrogens, which is 1 times 3. So that's 14, 17. So 10 divided by 17 gives me 0.588. And I've got a 4 to 5 ratio. So again, I need to get it into a ratio of 1 over here first. So I need to do 0.588 divided by 4. That gives me 0.147. And then I just times that by 5 to times it up on the other side. So I times by 5. That gives me 0.735. My relative molecular mass of oxygen is 16 times 2. That is 32. So I just times by 32. And that gives me 23.5. So my final is 23.5 grams. So 10 grams of ammonia is going to make 23.5 grams of oxygen. What mass of aluminium oxide is produced when 135 grams of aluminium is burned in oxygen? So I've got to find out the mass of aluminium oxide given 135 grams of aluminium. So I've got 135 grams of aluminium. My relative molecular mass of aluminium is 27. My relative molecular mass of aluminium oxide is 27 times 2 plus 16 times 3. That gives me, open brackets, 27 times 2, close brackets, plus, open brackets, 16 times 3, close brackets, 102. Right, now I can start doing my calculations. 135 divided by 27 gives me my moles of aluminium, 5. Now I've got a 2 to 1 ratio, so I've got half the amount of aluminium oxide, so I divide by 2, that gives me 2.5. I times that by 102, and that gives me 255 grams of aluminium oxide when I burn 135 grams of aluminium. Okay, what mass of iodine is produced when 7.1 grams of chlorine reacts with excess potassium iodide? Remember, if we see the word excess, we know we can just ignore the amount of potassium oxide that we've got because we've got way more than we can actually use. So in this case, we don't need to look at the potassium iodide. What we need to do is find out what mass of iodine is produced when 7.1 grams of chlorine. So the information that they've given us about excess potassium iodide is a moot point. I just plug in what I've got, 7.1 grams. Chlorine is 35.5 times 2, which gives us 71. I don't know, 355 gives us 71. And iodine is 127 times 2. 127 times 2. So 127 times 2 gives us 254. Now I can start doing my mole calculations. The reason why I do my MR over there is because then I can just keep my moles on my calculator, and it makes the sum a lot easier. It makes it flow a lot quicker. It also stops me from getting any kind of input error when I have to re-input my moles. So 7.1 divided by 71 gives me 0.1 moles of chlorine. It's a 1-to-1 ratio. So if I've got 0.1 moles of that, I've got 0.1 moles of that. I just have to times it by 254, and that gives me 25.4 grams of iodine, which is produced when 7.1 grams of chlorine reacts with potassium iodide. What mass of hydrogen is needed to react with 32 grams of copper oxide? Well, I'm working out the mass of hydrogen, and I know I've got 32 grams of copper oxide. So I've got CuO on this side, and I need to find out the mass of hydrogen here. The equation is balanced, so I've got 32 grams. The MR of copper oxide is 64 for copper, plus 16, that gives me 50. No, what am I talking about? 50. 64, 74, 80, that gives me 80. And hydrogen is 1 times 2, which is 2. So 32 divided by 80, and then that gives me 0.4 moles. It's a 1-to-1 ratio, so I've got 0.4 moles of that. I times it by 2, and that gives me 0.8 moles. Perfect. What mass of oxygen is formed when 735 grams of potassium chlorate decomposes? So I need what mass of oxygen? 3O2, and I need 2 lots of potassium chlorate. I just plug in what I've got, 735 grams of that. The MR of potassium chlorate is 39 plus 35.5 plus 16 times 3. That gives me 16 times 3. I'll do that first. That saves me using brackets. Plus 35.5 plus 39. That gives me 122.5. And my oxygen is just 16 times 2. That gives me 32. So let's start with what we've got. 735 grams divided by 122.5. That gives us 6 moles of potassium chlorate. Well, I've got a 2-to-3 ratio, so I need to do 6 divided by 2 to get 1 equals 3. Then we times by 3 because we've got a molar ratio of 3 over here. That gives us 9. So I've got 9 moles of that. I just times it by 32, and I get 288. Perfect. What mass of hydrogen is produced when 190? What mass of hydrogen is produced when 195 milligrams of potassium is added to water? So we don't care about the water at the moment because it hasn't given us the any information about the water. So we put in the two things it has told us about. We want to know the mass of hydrogen when we have 195 milligrams of potassium. So we've got 2K here. The relative molecular mass of potassium is 39, and the relative molecular mass of hydrogen is 2 times 1, which gives us 2. So, what mass? We've got 195 milligrams of that. Don't worry about the fact it's milligrams, just means our answer will be in milligrams. So, 195 divided by 39 gives us 5 moles. 5 moles times divide by 2 because our ratio is 2 to 1. So divide by 2 gives us 2.5 moles. So 2.5 moles times by the relative molecular mass of 2 gives us 5 milligrams of H2. How much calcium oxide is produced by heating 50 grams of calcium carbonate? So they're asking us to work out the calcium oxide, and they've given us the amount of grams of calcium carbonate. So we've got CaCO3 and CaO, 1-to-1 ratio. Nice and easy. So we've got 50 grams of that. Calcium MR is 40 times, no, not times 12, silly Mrs. Baker, 40 plus 12 plus 16 times 3. That gives us 100. I'm a nerd, so somehow I remember calcium carbonate. Nice round number. Calcium oxide is 40 plus 16. It gives us 56. So 50 divided by 100 gives us 0.5 or half a mole, 1-to-1 ratio. So if I've got half a mole over here, I must have half a mole over here. So I times by 56. That gives me 28 grams of calcium oxide. Here's another one. What mass of magnesium oxide is formed when 6 grams of magnesium reacts with oxygen? So I'm looking for the mass of magnesium oxide when 6 grams of magnesium reacts with oxygen. So I need to put my magnesium in here, 2 mg, and I need to put my 2 MgO for magnesium oxide. I've got 6 grams of magnesium. Magnesium's MR is 24. Magnesium oxide is 24 plus 16. That gives me 30. That gives me 40. So 6 divided by 24 gives me 0.25. I've got a 2 to 2 ratio simplified as 1 to 1. So it's the same. So if I've got 0.25 moles of magnesium, I've also got 0.25 moles of magnesium oxide. I times that by 40, and I've got 10 grams of magnesium oxide from my 6 grams of magnesium. What mass of carbon dioxide is produced when 56 grams of butene is burnt? Don't worry if you don't know what butene is, really doesn't matter. All I need to know is what mass of carbon dioxide when 5.6 grams of butene is burnt. So I look at my molar ratio and I'm saying I'm burning C4H8 because the question has told me the formula of butene, and I'm going to produce 4 times as much CO2 as given by my chemical equation. I've got 5.6 grams of that. My relative molecular mass is 12 times 4 plus 1 times 8. So 12 times 4 plus 8 gives me 56. And carbon dioxide is 12 plus 16 times 2, which gives me 16 times 2 plus 12 equals 44. So 5.6 divided by 56 gives me 0.1 moles. If I've got 1 mole of that to 4 moles of that, I must have 4 times as many. So I times by 4. That gives me 0.4. Then I can times it by 44, which is the relative molecular mass, and it gives me 17.6. So 17.6 grams of carbon dioxide is produced from 5.6 grams of butene. The pollutant sulfur dioxide can be removed by the air by reaction with calcium carbonate in the presence of oxygen. What mass of calcium carbonate is needed to remove 1 ton of sulfur dioxide? Again, I don't have to worry about the fact the question is quite wordy. I just highlight the 2 things that it's asking me about. So what mass of calcium carbonate? So I've got 2 CaCO3 according to my balanced equation by removing 1 ton of sulfur dioxide, and I've got 2 SO2s. Plug in what the question is telling me. It's saying I've got 1 ton of that. Doesn't matter that it's back to front. So I work out my relative molecular masses. Well, sulfur is 32. So I need to do 32 plus 16 times 2. And I need to do 40 plus 12 plus 16 times 3. That gives me 100 here. And that gives me 32 plus 32 gives me 64. So 1 divided by 64 gives me 0.015625. 625. If I've got a 2 to 2 ratio, simplified, that's 1 to 1, so I can just carry my number of moles over. 0.015625. I already got it on my calculator, so I just times that by 100, and I get 1.5625 grams, 1.5625 tons of calcium carbonate. Okay, here is the double stretch and challenge because it is a double step process. It's exactly the same step process, but it's a double step process. So it's saying calcium hydroxide is manufactured by heating calcium carbonate strongly to produce calcium oxide, then added a controlled amount of water to produce calcium hydroxide. So what mass of water would you need to add to the calcium oxide produced from 1 ton of calcium carbonate? So it's asking us what mass of water we'd need given that we've got 1 ton of calcium carbonate. And then it's saying a second question, what mass of calcium hydroxide would you ultimately produce from the 1 ton of calcium carbonate? That may seem really complicated, but we follow the same process that we've been working on all this time. Let's see what we need to do. So it's telling us we've got 1 ton of calcium carbonate. So we put that straight into here, 1 ton of calcium carbonate. The relative molecular mass of calcium carbonate is 40 plus 12 plus 16 times 3, which is 100. We know calcium oxide is 40 plus 16, so it's 56. So 1 divided by 100 gives us 0.1. No, 0.01, sorry. That's why we always use a calculator. We know we've got a 1-to-1 ratio, given our balanced equation up here. We've got a 1-to-1 ratio. So if we've got 0.01 moles of that, we've also got 0.01 moles of that. We times that by 56, and that gives us 0.56 moles of calcium oxide. Now we know we've got 0.56 grams of this. We know that we've got 0.01 moles. So we could bring either or down, it doesn't matter. So in this case, let's bring it all down. We've got 0.56 grams. We've got 0.01 moles. And we're going to assume that we can now react all of our calcium oxide. The MR is 56. So how many moles of water do we need? Again, it's a 1-to-1 ratio. So we've got 0.01 moles of that. The relative molecular mass of water is 1 times 2 plus 16. That gives us 18. So we do 0.01 divide by 18, and that gives us 5.55 grams. So what mass of water would be required? Oh, not grams, tons, sorry. 5.5 tons of water would be required. But then it goes on to say, well, what mass of calcium hydroxide? For that, you can just extend your table. So we're just going to extend our table here. Don't worry if it's not completely neat. Who cares? So now we need to find our moles of calcium oxide. Well, if we've got 0.01 moles of calcium oxide, 0.01 moles of water, we've got a 1-to-1-to-1 ratio. We know that because we look at this, 1-to-1-to-1. No big numbers to be seen anywhere. So that gives us 0.01 moles of that. Our calcium hydroxide, sorry about that, calcium hydroxide. So calcium hydroxide is 40 plus hydroxide is 17. So we've got two of them, 17 times 2. So 40 plus 17 times 2 gives us 74. So we've got 0.01 moles times by 74. That will give us 0.74 tons of that. So up here, what mass of calcium hydroxide would we need? We would need 0.74 tons. So it seems, on the surface, it seems difficult, but actually it's not that difficult at all.